Today we are gonna finish our discussion about diffusion models, and then we're gonna move on to a sequence of lectures on foundation models, large language model stuff. So today we are gonna talk about some of the general kind of like framework, the change of the paradigm, and some of the pre-ChatGPT or pre-GPT kind of like technology to some degree. We're going to spend probably one lecture about what happened before GPT becomes the most popular, the dominating approach. And then we're going to talk about, how do we train the autoregressive large language model, which is what GPT is about. And then we're going to talk about some of the post-training RL stuff for large language models. So this is probably a sequence of like 4 or 5 lectures. And in the middle, we are also going to talk about some of the RL stuff because you need the RL basics to even discuss how to use RL for large language models. Maybe in the meantime, we're going to talk about some of the robotics applications along the way as we define RL. That's pretty much the rest of the lectures. I think we have probably like another, maybe like 7, 8 lectures. And in the middle, I think there will be one lecture on the system perspective of machine learning, which is about how to use GPUs, how do you think about, actually the details is very complicated. There's no way we can even, I think even one course is not enough. So, but we have a guest lecture on how to think about some of the system perspectives, which is actually quite important, because all of these are massive scale. I think we have like I think you see, so Siren, I think she's gonna give a guest lecture, yeah. So I think right. So I think so for foundation. So okay, so that's the plan for the rest of the lectures. Okay, so let's start with diffusion model. I think let's recall what we have done last week. We have defined the diffusion model, the forward and backwards, right? So the forward is kind of like so you start from a clean image. The forward is kind of a bunch of like noising steps. You get x1, x2, up to xt, which is going to be just something from standard normal Gaussian. And this direction is q, x1 given x0, q, xt given xt minus 1. And we have a model that we parameterize to for the reverse direction, which is p theta xt minus 1 given xt. And this is parameterized by a new artwork. I think precisely this model, I think the parameterization we had was something like n Gaussian with some mu tilde t xt, sorry, not mu tilde, mu theta t, mu theta xt t, and with some covariance, let me see whether I have, I think the covariance is assumed to be beta tilde t identity. Right, so this is the parameterization for the reverse directions. And we also have established that if you maximize the you want to maximize the log likelihood of p theta x0, which is the marginal distribution of x0 under the parameterization theta under the distribution p theta you defined through this process. And then there's an elbow lower bound, which is to simplify. So we skipped the details, but we got this t free from 2 to t KL between q xt minus 1 given xt x0 and p theta xt minus 1 given xt. So, and minus KL between q xt given 0, p theta xt plus expectation log p theta x0 given x1 to t. So last time we only had time to discuss this term. This is a KL between two Gaussian distributions. One of the Gaussian distributions is this one, and the other Gaussian distribution, I think, probably if you recall, the other Gaussian distribution is xt minus 1 given xt x0. This distribution is equals to mu tilde t xt x0 with covariance beta tilde t identity. And then we discussed that at the end of the last lecture, these are two Gaussian distributions. If you look at the KL, it's actually just comparing the mean. Actually, we chose the variance to match. And that's why the KL between two Gaussian distribution is really just comparing the mean of the two distribution. So that's why if you call this term, I think notation we use is LT minus 1. So there's different t's, and we say this is the LT minus 1, and LT minus 1 is equals to basically comparing the mean of these two distribution. It's some expectation of 1 over 2 beta t tilde. And you look at the mean, the difference of the mean. This is the mean for the Q, and the mean for the P theta is mu theta xt t and do L2 norm square. So, and this expectation is over Q, meaning that strictly speaking, you are generating, because xt is a random variable, you are generating xt from Q. And for every realization or instantiation of LT, you have xt, you have two numbers, you compare them, you take the square, and you average over the choice of xt. So that's the loss function we derived formally from this lower bound. That's only one term, or one sequence of terms. That's the term for LT minus 1. Let's also discuss these two other terms very briefly. So this term is actually just 0, because if you, guys, I need to throw away this so that I don't get confused. So, this term is just 0 because we assume that t is going to infinity, and recall that pt, the distribution of pt assumes to be identity, the standard normal distribution with mean 0 and variance identity. And we established that when t goes to infinity, xt given x0 is also standard normal Gaussian, because you add too much noise so that you just, the noise just wash out the signal. So that's why both of these are the standard normal Gaussian. They have the same distribution, and the KL is 0. So this is 0. Or strictly speaking, this is converging to 0 as t goes to infinity. So we just assume it's 0. And this term is often in literature denoted as L1, because it actually does have almost the same kind of like almost have the same term as all the other LT term, even though like on the surface it looks different, but actually they have the same form of the same formula. So I think I will probably not go through all the details, but maybe let me show you the rough idea on how to derive this term. So in some sense, it's kind of like eventually you find out that it's almost the same as the LT minus 1 term. So basically the first thing to deal with, so this is for L1. So for L1, the first thing to realize is that p theta x 0 given x1 to t, right? So this thing is the same as p0, px0, p theta x0 given x1 because of the Markov property. You don't have to even look at any of the x2, x up to xt if you condition x1. So that's what the Markov property tells us. And and then you can just choose, we haven't actually even specified the distribution p theta for x0 and x1. We have specified it for a larger t, but for x0 and x1 we haven't discussed it. We can just write this. We can make the same assumption. Let's say this is n mu theta x1 1. Say sigma 1 square. I think sigma 1 square here is the variance. Then you know that you are just looking at the log likelihood of a Gaussian distribution, right? A log likelihood of a Gaussian distribution is pretty much just the you take the log of the Gaussian distribution density has exponential in it. Once you take the log, it's just really what's inside the exponential, right? So log of the density is really something like 1/2 sigma 1 square x0 minus mu theta x1 1 square, and plus some constant term. This is just because if you take exponential of this is the Gaussian density, and you take the log, this is the log, and you can see this term. And what is x0? So, and it turns out that if you do some calculation, you will find out that actually x0 is so x0 just is, you know, I think this is kind of like there's some derivations about this, but you can define x0 to be, let's say you just denote. So let's say suppose you define mu1 tilde x1 x0 to be equals to x0. Suppose this is your notation, then you see that if you put it here, it's the same formula. So this is 1/2 sigma 1 square mu1 tilde x1 1 minus mu theta x1 1 square plus constant. So now I have the same formula for t is 1 or t is 2, right? So and the only thing that remains to be checked is that whether you have the same interpretation of these two things, right? Like, you know, you can define whatever you want with mu1 tilde, but actually is this like the same formula? So it turns out that actually it's the same formula because this x0 is equals to, so x0 is actually equals to x1 minus square root 1 minus alpha 1 bar epsilon 1 hat square root alpha 1 bar, which is equals to x1 minus square root beta epsilon 1 hat over 1 times 1 over square root alpha 1. So and this is the same. So if you equate this two, this is the same formula as all the other definitions of mu1 hat. So recall that mu t tilde for t is larger than 2. Mu1 t tilde, the definition is, I think we gave this last time. This is the mean of this distribution Q. Let me find out the definition. So for t is bigger than 2. So basically for t is bigger than 2, this is your formula. And now for t is 1, this is your formula. So they have the same formula. So in some sense, there's a clean way to just organize everything into one formula. So basically for any t, the LT minus 1 just equals to this. So this actually, before we only say this is for t larger than 1, but actually now it also works for t is 1 and t is larger than 2. So both have to share the same formula. So that's just why it's kind of like a very clean, you know, it's, in some sense it's kind of like, there's some fundamental reasons, but you can also just treat this as a coincidence because it's just on the boundary it's a little bit different, in terms of the notations, but fundamentally it's the same thing. Cool. So in some sense, that's what we should remember. So basically the loss function is just that we are trying to maximize minus sum of LT from t is 1 to t minus 1. And each of these terms is like this. So maybe let's write this way. T is actually t0, I guess we can write t is 1 from t minus 1 and t minus 1. And each of these terms, the definition is this. And it's some kind of coefficient. And actually, maybe there's another small caveat, which is that if you really look at the empirical stuff, then people don't actually use these coefficients. So there's some coefficients here, there's some coefficients here. People just drop all of these coefficients. They just say, in practice, let's just only define LT minus 1 as the expectation without the coefficients, just the differences between mu tilde t, xt x0 minus mu theta xt t. Yes. So this is the in practice how people choose the loss function. I guess I'm saying that each of these terms is defined to be LT minus 1 is defined to be this. So you maximize the minus of the sum of the square terms, which is the same as minimizing the sum of the squares. So, and you can interpret this, I guess let's just try to reinterpret this again. So what is mu theta xtt? Mu theta xtt is, under my model, what's my prediction of the mean of xt minus 1 given xt? So mu theta xtt is how I would reconstruct xt minus 1 given xt, right, under my model. And what is mu tilde xt x0? Mu tilde xt x0 is the mean of this thing, q xt minus 1 xt x0. So, and what is that? That's how the true process will reconstruct xt minus 1 given xt and x0. So basically, you know both, under the true model, suppose you know both xt and x0, how do you reconstruct xt minus 1? And it happens that actually the reconstruction is very simple. It's just a linear interpolation, right? Like, because we have seen that the derivation tells us that under the true model, to reconstruct given xt and x0, the best way is just to do this linear combination of xt and epsilon high t, and epsilon high t is actually a linear function of xt and x0, right? So I think probably you have remembered some of this, like epsilon high t is actually the differences between xt and x0. So basically, this whole thing is a linear combination of xt and x0. So you are basically reconstructing under the true process, this q under the true process is just reconstructing by doing a linear interpolation between x0 and xt to reconstruct xt minus 1. And you want your reconstruction to match that. And that's pretty much what it is. Yeah. Any questions? So this is a fully implementable algorithm in the sense that you can just sample xt, right? So this expectation is over the randomness of xt. So xt is sample from q, sample xt by choosing, by applying the noisy function, the noising process for t steps, and you get some xt, and then you compute this, which is a linear combination of xt and x0 by using this formula, and then you apply on your network and get this. You can get the loss function, and you do backpropagation, and you minimize the loss. So that's how you train this. And then next, I'm going to spend probably another 5 minutes to talk about how actually people do it in practice, with a slight modification of this. So in practice, people actually also kind of like reparameterize this a little bit, just to simplify the formula. So the trick is that so this is probably what you will see from most of the materials. So so you can actually I already gave that. I'm not sure whether I review it too fast. My bad, let me. It's a little bit challenging because I think I need to remember exactly what we give, and with some repetition, I need to repeat some of the previous lectures, but not repeating everything. So that's why it's a bit confusing. So I think I already wrote there, but maybe just to recall, I think last time we definitely give this version of the mu t tilde. So the version that we give is that, or maybe we didn't discuss this, I think last time. Okay, so maybe that's some of the people's confusion, right? So how did we derive this formula for mu t tilde? So maybe let's discuss that a little bit. So how do we get this q xt minus 1 given xt and x0? So why this is a Gaussian and how do we derive this? The main reason is that xt given x0 is Gaussian. And jointly xt minus 1 given xt given x0 is also Gaussian. And xt minus 1 given x0 is also Gaussian. So everything given x0 is Gaussian. So in some sense, you just assume condition, you always have conditioning on x0. Then the joint distribution, the marginal distribution, everything is Gaussian. So when everything is Gaussian, then all the conditional is also Gaussian. So basically, if the joint is Gaussian, then any conditional is Gaussian. So that's why both xt minus 1 given xt or xt given xt minus 1 are both Gaussian. And you can actually, I think in the lecture notes, we have some formulas for this. So basically, if you know A and B are jointly Gaussian, and then you can have formulas for A given B and B given A, and what's the mean and variance for both of them. And you can just plug in that. So that's how you compute the mean and variance of this qxt minus 1 given xt and x0. So basically, you just say A is equals to this, and B is equals to this, and you know A and B jointly is Gaussian, and you can plug in the formula for both of the two conditionals. And that's how you got how we got the formula for mu t tilde x t x0. And it turns out that, you know, the formula is very simple. It's something like some linear combination of the coefficient is kind of complicated, but that's just some coefficient, some scalar. But fundamentally, it's just a linear combination of x0 and xt. And recall that xt is under our formula, I think xt is alpha bar t x0 plus 1 minus alpha bar t, or maybe beta bar t. I think we use 1 minus alpha bar t plus 1 minus alpha bar t epsilon t hat, right? So you can, I think if you remember, like we can roll out all of the noise so that we can add up all of the noise so that we add all the noise into one noise vector. And so then xt is equals to some scaling of the original data plus a noise vector. And then you can plug in this to this. So you can basically replace xt by you can replace x0 by xt because they're all linearly related, so that you can get rid of x0 and you can get that formula. So you can get, if you plug this in, and you can get this is equals to one over square root alpha t xt minus beta t square root 1 minus alpha t bar epsilon t hat. And recall that epsilon t hat has this standard normal distribution. They are not, for different t, the epsilon t hat are not IAD, but they are correlated, but each of them has marginal distribution. So basically, this is my mu t tilde. I have some formula that only depends on xt, but not x0. It depends on xt and epsilon t. So, and then, in practice, what people do is that people say, let me also parameterize my neural network because xt is known, right? So in some sense, like one option is I can just parameterize I can try to light my neural network to directly predict this. That's what we are doing, right? But the xt part is already known. So why not parameterize the neural network to also incorporate the part that you already knew? So that's why people say, oh, let me parameterize my neural network with the same formula so that I don't have to match the part I already know. I just hard code the part I already know. So in your parameterization, you write the same thing. So 1 over alpha square alpha t xt minus beta t 1 over square root alpha t bar times epsilon theta xtt. So this is my neural network, and then my mu theta is another composition of my neural networks with some other formulas, right? So which is known, right? So I know this, so I'm just going to hard code it in my formula, and only the part I don't know, I'm going to use the neural network to predict. And if you reparameterize this way, then you can see that mu tilde t xt x0 minus mu theta xtt, this loss function that we care about, if you subtract these two, right, you're going to cancel out everything, right? The only thing that you have is some scalar times the difference between the two epsilons. So this will be some scalar coefficient, which is beta t squared 2 beta t tilde 1 minus alpha t bar alpha t times the expectation. So basically you're just comparing whether you can reconstruct a noise. Recall that what is epsilon hat t? This is the noise you added to get xt in the first place. And now you are saying I'm going to use this neural network to predict what was the noise I added in the first place. And if they can match, then you get perfect reconstruction. Or maybe noise kind of prediction. So basically you turn this reconstruction into a noise prediction problem. So and then people drop these coefficients and only focus on this. So it's a very clean formula. You just look at what is the noise you added, and then you try to use the network to predict the noise. And so basically the algorithm eventually is simply the following. So finally the training algorithm is just that you first sum 1, you sample some x0 from the data set. From training set, and then you sample t, a time step t, say uniformly from 1 to t, because you have a sum over all of these terms, right? So you sample one of the term, it's kind of sarcastic with inside. You really objective is sum of the t terms, capital T terms, and you sample one term. And when you sample one term, maybe this is the term you sampled. And then what you do is you say, I'm going to get epsilon high t from standard normal Gaussian. This is the noise I get. And then I construct xt by this formula, or come to the formula we had, which is a linear combination of x0 and the noise vector, and then I have a neural network. So this is a neural network, epsilon theta xtt. You apply a neural network on your data, and then you define a loss function. The loss function lt theta is equals to this epsilon height t minus epsilon theta xt t. And then you minimize this. You take the gradient of this and you update your parameter after that. And if you look at most of the materials, they actually don't even write epsilon t hat t, because in some sense the indices doesn't really make like any additional differentiation power. So because you can just write, you just sample epsilon, then the notation doesn't have to even have the index. So that's why in most of the materials you just say epsilon is sampled from this, and then you add epsilon to this, and then this is epsilon. So because anyway it's a random variable, it doesn't really matter how you name it. So that's the tuning algorithm. And then after you train this, you get this model, which is the model that is trying to reconstruct a noise. And then how do you, the way that you apply it to generate is just that you run this p theta from the right hand side to the left hand side. So basically, sampling just mean that you first sample xt from the noise, And then for each step, you first compute, you already have the theta, right? You compute epsilon theta xtt. And then you try to decode xt minus 1 using a formula that you just add back the noise. So wait, let me see whether there's a, sorry, I'm missing one step. So you compute this, and then you compute the mu theta using the formula that we had. So mu theta is just a linear combination of xt and epsilon. I guess I'm just rewriting that equation. And you get a mu theta, which is your prediction for the xt minus 1, the mean of the prediction of xt minus 1. And then you just say, I'm going to take xt minus 1 is equals to the mean plus some noise, because even the reverse process still has some noise, where the noise is sampled from 0 and t. I guess sigma t is the variance you chose. I think in our cases, we chose sigma t to be square root beta tilde t. We already chose that. So strictly speaking here, I should write square root. If I already chose that, I'll choose this to be square root beta tilde. Sounds good. Any questions? I think we have discussed why diffusion model works better. They are not kind of like a very strong theory to prove everything, but generally speaking, I think the main intuition is that one thing is that in one direction of this process is known, is a fixed noising function, so that you don't have to parametrize both the forward and backward. So that seems to make the optimization and everything much easier, because before people have tried to use parametric functions for both sides. Of course, at the cost is that you have to stretch the timeline to be longer, so the t is actually big. So at the beginning it's 1,000. But I think that actually has a benefit, because when you stretch the timeline, the reconstruction becomes locally easy. Like each step, you just have to remove a little bit of noise. So, and so basically at the beginning, you just have a purely white noise image, and then you just have to remove slightly noise to make it slightly, like have some kind of slight kind of signal, and then you try to make it sharper and sharper, at the beginning, you only have to get the contour and the rough idea of the image, and then gradually you sharpen, so on and so forth. So in some sense, you add more and more details through this process. And each of the local steps is somewhat easier to learn. And that's how you make it, kind of like, eventually everything is about how easy it is to learn this, right? Fundamentally, you should be able to use networks to represent everything, but how do you represent still matters, and how do you learn matters. And this is a way to decompose the big generation task into smaller steps so that you can learn more efficiently. Okay, great. So, if there's no any other questions, I'm going to use the rest of the lectures to talk about as a kind of overview for some of the foundation model stuff. So, sure, of course.
I'm trying to understand this already now. So, we learned the parameters here, and the parameters we're learning those are I'm a little confused, I guess, on how the parameter update is happening. I don't see that step anymore.
Oh, I didn't write it explicitly. So yeah, so that's a good question. So basically, once I define a loss function, everything is computed, right? So computable. So I have a new network. This is known, this is unknown, and I can apply it and define it in PyTorch. And then you compute the gradient of this, and you take one gradient step update. You can use item, gradient descent, so on and so forth. Yep. Any other questions?
It's actually finding a loss function is like a main thing
for this lecture, yes. I think in some of the other lectures we spend more time on how to compute the gradient, for example, right? So there's one lecture that is entirely about how to compute the gradient. You have to apply those backpropagation auto differentiation here, because how to compute the gradient here, you have to apply the same thing. And I think in Chris' lectures, I think he talked about SGD, and I think I also mentioned some of the SGD stuff, right? So those are, those are also needed. It's just it's a whole stack, right? There are so many components, and yes, if you have a new, kind of application or new algorithm, then often it's on the loss level, right? But you could also innovate on the optimizer level, say replacing SGD by some other optimizer, so on and so forth. And then those changes are often universal, you can apply it for, if you change the optimizer, you can do it for diffusion models, you can do it for large language models, you can do it for maybe linear regression as well. So those are a different layer. Yeah, but generally I think for the rest of the lectures, we are mostly talking about the data, the architecture, the loss function, and the training procedure, right? Not much anymore about computing gradients and how to update gradients. You just assume once you define a loss function, you can optimize it. Cool. So I think now let's talk about a foundation model. I think this is a term that actually is a term that is kind of coined by one of the papers that many of the Stanford people wrote about, now probably about 5 years ago, maybe 4 or 5 years ago. So I think the story was that I think after GPT-3 came out, I think that's 2020 summer, I remember we were very some of the faculties in SAIL were very excited about it. I think we discussed a lot about this is actually I've seen so many faculty actually sitting in one room and playing with the OpenAI playground. At that moment, OpenAI doesn't even it's not ChatGPT. It's just a playground with one text box, and what you write and what model generates actually are written in the same text box. So and you can there's some kind of you can choose some kind of hyperparameters there, like the temperature, so on and so forth. On the right hand side, you can choose the model with a drop down menu. That's those kind of things, and we play with it, and I think many people are very excited about it. And then I think Percy Liang, so he led this team to study this new paradigm, because we kind of realized that this is a new paradigm of machine learning that is quite different from the deep learning wave. And we wrote a survey paper, and we call it foundation model. And in that paper, I just checked yesterday. I think that in the abstract, it's written something like this is an emergent paradigm. And I look at my notes, in my lecture notes, I also call it emergent paradigm. But I think after 3 years, we probably should just not call it emergent paradigm. It's the new paradigm. It's the new paradigm. So and also this paradigm, also there are many variances in some sense. 5 years ago, when we talk about the paradigm, we actually including actually a broader set of kind of techniques in some sense, and now some of those are a little out of date to some degree, and we are converging to even a smaller paradigm to some degree. But nevertheless, I'm still gonna talk about some of the techniques that were popular around 2019 to 2022, let's say, before ChatGPT came out, for 1 or 2 lectures, and then we're gonna talk about things that are the dominating approach after 2022, let's say. So. I think the key kind of word here is the so-called pre-training. Probably you have heard a lot. And now there's a new word called post-training, which we'll discuss in later lectures. So in some sense, this foundation model paradigm, I think in the survey paper, we discussed there are 2 phases. In some sense, the first phase is the pre-training, the second phase is the adaptation. And adaptation phase. And what happens is that pre-training, the real difference here, you can there are many kind of like different aspects, but probably the most important thing is that it's often using massive unlabeled data. And, often several magnitudes higher than, what people have done before, massive unlabeled data. And also, this is also kind of somewhat general purpose. You don't really actually just only focus on one type of data. Your data is very diverse. You just try to download everything from the internet. And you don't necessarily care about even data quality that much. Of course, it matters, but at the beginning, people just download very brute forcefully from internet. And some of the data actually we look into it. It's not even, you have 100/n consecutively in some of the documents that's even possible. But that's fine. So eventually, the first few versions, the data, they are trained on is actually pretty messy. And eventually people clean up the data, and it's better and better. So the gist is that you have as much data as possible. You probably, at the beginning, you don't even care about the quality that much. You just get massive unlabeled data, and you don't care about the labels, right? You just download documents. And some of these are HTML files, which all the HTML text in it, and some of these are Word documents, some of these are other kind of documents. Everything is fine. So, and then, in the adaptation phase, you can adapt to many tasks, adapt to a wide range of tasks. So in some sense, the key thing is that you start with a very, very, I think that's the reason why it's called foundation model. So you start with a very good foundation, and then you can kind of adapt to different tasks. You never just directly go deal with one task. Before this, mostly people are just say, yeah, I have image classification. I just train on image classification. If I care about object detection, I just train on object detection. And some people actually do multitask. They say I have 3 tasks: object detection, image classification, maybe bounding box kind of a detection, all of this. And I train these 3 tasks, but only 3. Here, the number of tasks is kind of unlimited in some sense. You can have even the GPT paper probably have 100 tasks in the evaluation, and sometimes even more than that. And now it's even crazier. You don't even have sometimes the notion of tasks is even defined just because you have so many of them. You cannot even just distinguish what is a task, what is kind of a domain in some sense. Just basically the number of tasks is just way too many. Okay. And for the adaptation phase, in 2021, I think we discussed a lot about there are several different settings for actually, there are also different type of pre-training algorithms. We'll discuss a few of them. Of course, the most obvious one is the next word prediction laws with the large language models. But today, I think we're going to discuss a little more about adaptation first. So for adaptation, the type signature is that there are 2 things you should discuss, right? One thing is that how much data I have to adapt to a new task, right? And what type of data. And another thing is that, what's the technology to adapt. So maybe let's talk about data part, right? So the adaptation phase, in 2021, 2022, I think, people still, care a lot about this kind of you have a labeled data set, a labeled downstream task, downstream data set. So you have something like X task 1, Y, you have these pairs. So you have n of these tasks, data points, and they are labeled. Why is the label? X is the inputs, and if n is small, let's say 5 to 10, maybe, then you call this few shot. So, and one of the real breakthrough, for GPT-3 is kind of you don't have to actually do even few shots sometimes. You can even do 0 shot. So, and now at this moment, I think people mostly think about 0 shot. Almost nobody collects, downstream labels anymore, to adapt your model. You just do 0 shot. Basically, 0 shot just means you don't even have to adapt. You just, in some sense, you just describe your tasks. You say, this is my task, please solve it. You don't have to collect any new data for the tasks, for the downstream tasks. But in 2021, 2022, or maybe 2019, this is a few shot or maybe even more labeled downstream task is the more dominating approach. So for example, you train a model and then you say, I want to apply it to sentiment classification. And then you collect a small data set, sentiment classification data set, and then you fine tune, I haven't really defined fine tune, but you fine tune on this small data set, let's say sentiment classification data set, and then your model can work on sentiment classification. So that's the definition of few shot learning. And if you have any zero, then it's called zero shot. And then another thing is that, so whether when in this adaptation, how do you update your parameters or not? So, in this lecture and next lecture, I think I'm going to discuss those ideas where you actually do update the parameters with the data. And later on, we're going to talk about those cases where you don't have to even adapt it, change your parameters. You just prompt the model to adapt to the new tasks. Okay. So that's the high level overview. It's actually very simple, nothing complicated. And you can try to formalize this, but it's kind of like actually pretty, trivial to write down some equations. Basically, your pre-training, you have a loss function, maybe something like a pre-training loss function. And, for each data point, maybe you have data point I, you have some parameter theta, and your loss function is just the sum of the loss functions with the average. The only thing is that for pre-training, okay, there's no label, and also you have a very, very big N in the pre-training. And we're going to discuss, what are the loss functions, later. So, okay. Any questions so far? This is very, it's supposed to be very high level and nothing deep at all. So, but, yeah. Okay. So, next I'm going to discuss some of the somewhat generic way of doing the adaptation. So especially with a label data set. So if you have a label data set, downstream data sets, what's the typical way to do the adaptation? And to introduce some of these ideas, we probably have to introduce this idea called representation learning, which is still kind of relevant in many cases right now. So representation learning is, in some sense, a special type of pre-training where you pre-train a representation. So you are not pre-training a chat model like a ChatGPT. You are pre-training a model that represents the data. So what does that mean is that you train a model that's called phi, which is parameterized by theta. So this is it maps the data into some m-dimensional vector, and this vector. So I guess let's write this. So you have a data point x. You train a model, and this model is parameterized by some theta, and it outputs a vector in m-dimensional space, and this vector is called, either representation, sometimes it's called feature, sometimes it's called embedding. And you can design a loss function that train this kind of like representations, which we'll discuss next lecture. And once you get this representation, you do some training where you get some, say you minimize some loss function. Often the loss function is still like something like this, some loss for the data point xi and theta. And then this will give you some theta hat, which is a parameter that you obtain after the training. And then this theta hat will define a representation function, phi theta hat, which you can apply to get a vector out of any data point. So, and then once you have the theta hat, which is a trained representation, then you can use it to solve a downstream task with linear hat. So this is the concept so-called linear probing. So, and this is still a useful techniques for mechanistic interpretability of large language models. Even you don't use it for solving the tasks, you can still use this as a way to interpret or understand to some degree how the large language model works. So, but in the context of representation learning, linear probing is a way to even solve some downstream task. So what it means is that once you have this fixed embedding model or representation model, this is a vector, and then you have a new so-called linear head. So the linear head is a vector W in the same space, and you take the inner product of the linear head with the so-called feature or the representation, and this is your prediction. And maybe sometimes you have to do a softmax for predictions classification, but this is the core model. So basically you are just doing a linear model on top of a fixed representation. And then you can just say, if it's a regression, then you can just minimize, for example, say minimize over the linear head. You do 1 over, and let's say you have n task number of examples for the downstream task, and you do a simple regression loss. Of course, you can also define analogously some of the other classification laws as well. So here the theta hat is fixed, and this is a fixed vector. The only variables here is the W. You just want to learn W that fits your data as much as possible. So basically, this is just a very simple regression task once you pre-train the model. And people have realized that this is much better than just training, handcrafting some features or just training a linear model on top of X task. Because the representation is actually a very good representation that captures some semantic information in the data. So basically, without a transformation, your Y is not a linear function of the X. But now you transform it in a way such that you capture the important information linearly, so that you can linearly combine your new features or representations, and this prediction for Y can be much more accurate. Yeah, of course. Yeah.
We haven't talked about how we're learning
the representation. Yeah, I haven't talked. Yeah, I think that's a different. I'll talk about next section.
Are the foundational models made for different domains, or there's only like universal what we see?
Yeah, things are changing over time. 3 or 4 years ago, I think people have different techniques for different domains to some degree. But for vision, you learn the representations in one way, and for language, you learn the representation in another way. But now more and more people are trying to get multi-modal capabilities. So you want one model to be able to deal with both vision, language, maybe even videos. So then, in some sense, you have to have a unified approach. So I think in 2026, many of the models are, I think people call it omni-modal or multi-modal model, which just means that you try to take in both the images and text, so all of those in one model. What we're going to discuss, we are still somewhat at least for 1 or 2 lectures, we are still going to be domain specific. I think in this this kind of things probably happens more for, this representation learning happens more for vision domains, where you learn the visual representation first, and then you apply your linear classification. I think people are still using this for maybe, medical imaging. You first get the representation, and then you apply the linear classification for many different type of medical imaging tasks. And you have a small data set for each of the imaging tasks, and then you train a small linear head on top of that. But for the frontier models and frontier labs, I think it's often a universal model that takes in everything. Does it make sense? Yeah. So, and one other ways to adapt to a new task is so-called fine-tuning. the difference between linear probing and fine-tuning in this context is just very simple. So here you optimize only W, but not theta, right? But you can also optimize theta. So what you do is you say, I'm going to do the same thing. Maybe I'll just save some time to not rewrite the same equation. Let's say, let's use the color to change so you just do this, minimizing over the variable theta. And then you say here, this is not a fixed theta, it's actually a variable theta. You can vary. And you also initialize your theta to theta hat. So the initial theta hat, what you obtained before is your initializer. And then after that, you optimize both W and theta. And what is W initialized? W is often initialized somewhat randomly. Of course, there are still some variance about how do you exactly initialize it. And then you optimize both theta and W afterwards. So in some sense, if you think about this, it's kind of the interesting part about this is that the final loss function you are choosing here, like in some sense, the loss function itself doesn't have anything to do with the pre-training, right? Like you could imagine that I can just optimize the same loss function with random W and random theta at the beginning. And then there's nothing to do with pre-training. You are just training from scratch, optimizing a gigantic model for both of the two parameters. However, somehow if you initialize this part of variable with a pre-trained model, you get much better results. So if you think about that, it's kind of interesting because it's the same loss function, just the initialization are different. So somehow initialization affects your final global minimum. And that's actually proof that this loss function has a lot of global minimum. Like you can find maybe millions, of global minimum, and not all of them are the same. If you use training from scratch, you start from somewhere, right? Like some random place, and you find one global minimum, which is not very good. Or you can use another initialization, and you can find another global minimum, and that one is better. Of course, better or worse is also needs to be clarified, because here by better or worse, I mean the test performance. In terms of the training performance, I think you always get to 0 almost, because you don't have a lot of data here. So basically there are multiple global minimum of this loss function. And in terms of the training loss, they're all 0. But in terms of test performance, some of them is much better than the others. And how do you find the better ones? You have to start with a good initialization.
So we are like pre-training this representation. I'm trying to understand what exactly is the final output of this pre-training. Like, what are you learning here? Like,
we are learning a function. We are learning a parameter theta. So basically, the deliverable here is the theta hat, which is a concrete set of numbers under this architecture. Yeah.
And then the way that we are using theta to represent x, that depends on the modeling, that can be any kind of modeling that we.
Yeah. So there, it can be any, yeah. So, you still have to use the same modeling, but you cannot interpret the numbers in theta hat in a different way. It's still the same architecture.
The architecture, which is like.
The structure of the neural network.
Right. Okay.
Yeah. So you first predefine a structure for a network, but you don't know what the parameters are, right? You only know the structure, and then you try to find out the parameter, and then use that learned parameters to compute the representation.
So when we are applying the representation to a specific task, why is it reasonable to assume that the dependence on the representation is linear?
No, there is no, that's a great question. It's not exactly an assumption, because when you pre-train, we haven't discussed this yet. When you are training these models, actually you try to make the representation linear. Like the loss function, I didn't tell you what the loss function is, right? So next section I will tell you one example, and you can see it's kind of like you are trying to make it linear. So at least you are trying to make it usable in a linear fashion. So that's why it's somewhat linear.
Follow up on this one. So are we minimalizing it together or alternatively? Because if we do it together, then it won't be linear, right? Because we have
Yep.
time difference.
That's right. So if you only in a linear probe, you only have one variable. There's no alternating anyway. It's linear. And then when you do fine tuning, you jointly tune both of them. So it's not linear anymore. And actually, so this actually there's also a technique called LPFT, which is actually probably the dominating approach right now. If you really want to go this route, of course there are many other routes, but locally here this is a good idea, which is the following. So LPFT means that you first do linear probe, as the name suggests, it's a linear probe, and then fine tuning. What does that mean is that you first do linear probe by only optimizing W. So let's say maybe this is a loss function LW theta, right? Let's say let's denote this to LW theta. The first thing is you minimize over W and you put the theta part to be the initialization of the representation. So this is the LP part. And then maybe you get, maybe this will give you maybe W, let's say 0 and theta hat, right? Theta hat didn't change. And you get a new W0, which is the initialization. And then you do the FT. So basically you just keep minimizing both W and theta, this thing. But initialize with the W0 and theta hat. So, why this works better, I think it's a little bit hard to explain. I think, we don't know exactly either. There are some theory about it. But roughly speaking, I think if you use a random vector in fine tuning, you have both W and W is random and theta is fixed. Theta is kind of like the prediction model. Sometimes the random W will destroy the representation a little bit. So it's better probably to just first fix theta hat and then do some, you first make the W and the theta fit together and then you optimize both. When you optimize both, you do change the representation, but the change of the representation after the LP step, is smaller, compared to you just use the random weights. Anyway, so that's, another, approach. Let me see. I have 10 minutes. Let me see. So maybe in the next 10 minutes, let me discuss, another, generic kind of like a adaptation technique, which, is called, LoRa. I think this is something you probably should, at least you should know this, even though it's probably only useful for certain cases. So it's called LoRa or low rank adaptation. And this idea is kind of like agnostic to exactly how you adapt. As long as you are minimizing some loss functions in adaptation, you are not just doing zero shot, then you can apply the LoRa. So basically, the idea is that, for example, when you do this fine tuning, you are changing the theta, right? All the parameters in theta. So the theta often is kind of like a very gigantic model, right? The prediction model is also very big. But you only have like a small number of like downstream data points. And you are not really trying to change your prediction model by a lot in some sense, because the prediction model is very powerful. You are only adapting it a little bit. As the name suggests, adapting means you don't have to change much. So in some sense, it's questionable why you have to change so many billions of parameters to do your task. Maybe you just have to change a little bit. Like, there is no need to change everything. So, and also if you change every parameters, maybe it's kind of like, you are more vulnerable to overfitting, so on and so forth, right? So, and at least it's kind of like overkill to some degree. So that's why people say, oh, maybe let's not change all the parameters, or at least not use all the degree of freedom. It's very hard to say, oh, I'm only changing a subset of parameters, because you don't know which subset you should change, actually, right? It's all matrices, right? So, and so that's why the solution is that you say, I'm not going to change, I'm going to add a low rank update I'm going to restrict the degree of freedom, even though I change all the parameters, but I restrict the degree of freedom in my change. So in some sense, it's kind of like if you have a matrix W, right? So, if you fine tune it, you're going to change all the parameters here, right? But now you say, I'm going to reparameterize this, model to be W plus A times B. If W is like this matrix, and you say, I have a W plus, A and B like this. And its inner rank is R, which is low rank. So, which is small. So basically, A and B has much fewer number of degree of freedom than the whole matrix because, if you think about it, suppose you have a N by D matrix. Before you have D squared degree of freedom, and now you have DR, 2DR degree of freedom. If R is much smaller than D, maybe D is like 1,000 and R is only 10, then 2DR is much smaller than D squared. So you say, I'm going to only restrict my update to be A plus B, so A times B of this form, this restricts the degree of freedom in my change. So in some sense, it's kind of like as opposed to you minimize the loss of W, right? So this is what you do before. Let's say in adaptation, now you say I'm going to minimize L of W plus AB, where W, maybe let's say this is W0, and then you minimize over A and B. Right? So before you are minimizing over W, your W. So in this case, so maybe let's say, so you say your W is initialized to be but W0, which is what you trained before, and then you minimize W, right? That's the typical fine tuning. And now you say, I'm gonna fix W0, and I'm gonna minimize over A and B. And I can initialize A to be 0 and B to be some random matrix, so that initialization is the same, because if A is 0, then W0 is same as W0 here at the initialization. And then you only minimize over the two variables A and B. So that's called low rank adaptation. So this.
And the reason we have B and B is just for like is just for dimension purposes. Like why do we just have like one? Like we just wanted to add like we wanted like a D by D matrix, I guess, but after multiplying, that's why we have.
Yes. So if you just have one matrix, then it's D squared degree of freedom again. So that's why you have this low rank parameterization to make the degree of freedom much smaller.
But then we are also adding some bias, kind of symmetrical bias. Because we are doing a cross product there.
That I don't think so. Because A and B are not equal, right? So in some sense, you're just saying it's low rank. I'm not sure there's additional symmetry there. Yeah, it's just low rank. But low rank is a bias, So I think the question, the question is why we are doing this. So you restrict the degree of freedom you are changing. So, do you save something here? Like, do you save maybe let's examine one by one. So what do you really care about? So do you save the compute? Is it faster to optimize this? So it's less number of parameters, that's true. The less number of parameters to optimize, but it's not necessarily faster because you still have to use the W0, right? The forward pass still have to compute W0. So maybe let's just, so in the forward pass, you still compute W0 plus AB, and maybe you multiply this with a matrix, with a vector X, right? Something like this. And then you have many layers like this. So you still have to compute W0 times X. There is no way to save that compute. And that is the bottleneck, right? This A plus B, this part is cheap, but this part is still the bottleneck. And when you do the backward, you still have to compute W0 transpose. Remember that the forward pass is W, the backward pass is actually some kind of like matrix. You multiply the transpose of the matrix, right? So that still has to be done. So largely speaking, your compute don't really change much. There is some nuances about, how do you update how do you compute the gradient of the weights? That part you actually, the derivative with respect to weights. I'm not sure whether you remember, in backpropagation, there is a derivative with respect to the activations and derivative with respect to weights. These are two semi-parallel kind of type of computations you need to do. For the derivative with respect to activations, you don't save anything. at all. And for derivative with respect to weights, you do save a little bit because your weights are smaller and your by weights I mean the parameters, right? So your parameters have smaller number of parameters, so your gradient is smaller. So, but largely speaking, you don't save much for compute. So compute we don't save much. For memory, do we save? So it's, it's not exactly, I saw it, thanks. Yeah, but, it's not exactly in the sense that you still have to put W0 in your memory, right? Your memory for the parameters is smaller, but you still have to put these frozen weights in the memory.
You have to keep track of some momentum of the parameters and all that stuff takes a lot of space.
Exactly, that's great. So I guess just for some context, what you have to put in your memory when you do gradient descent. You have to put your parameters in the memory. You have to put the gradient in the memory, most likely. You have to put the momentum of the gradient in the memory. I guess we didn't discuss the momentum, which is something that you have to keep track of in your optimizer. And typically the gradient and the momentum actually cost much more than the number of parameters. I think it's kind of a factor of 12 or something. So basically if your model weights cost D numbers, then your gradient in the optimizer state on the momentum is probably something like, is it really 12? I forgot. It's maybe 6 or some constant factor, large enough constant factor for you to care about. So yes. So for those things, you don't have to save the momentum or the gradient for W0. You only have to save the momentum for AB, right? So that's why you save. However, the momentum and gradient, I guess this is a little bit of a system. I don't expect everyone knows this. The gradient and momentum are always kind of sharded across GPUs. For some scale, when you have more than one GPUs. So you never save the full gradient, or the full momentum, on each of the GPUs. So in this kind of parallelism, a typical kind of parallelism is called FSDP, data parallelism, where, the model parameters are duplicated across GPU cores. But the gradient and the momentum are not duplicated across all GPU cores. The gradient and momentum, because they're too big, actually, you have to kind of shard them. Shard them means you store different blocks of gradients on different GPUs. So in some sense, those are not always the bottleneck anyways. They are already sharded. So the saving here is, there is some saving, but it's not like a day and night to some degree. So, and what else? I guess we talked about the compute, the memory, and also this depends on whether you are doing training or inference. But I think all of the arguments are still largely true even for inference and training. In my opinion, one of the major saving for LoRa is that, there's one very most typical case is that you just don't have enough, you just barely have enough memory to, to do this. So that any saving helps sometimes. Because for example, sometimes you just, you are very tight in memory, and if you save even 10%, you actually can use one GPU as opposed to two GPUs. That's one case that is really, really important. But those are only when you have a very limited number of GPUs. And another one that I think is very important case is that when you have this LoRa, you can let multiple users to share the W0 and save many, many copies of the low rank part. And this is, in my opinion, probably the main reason why, for example, if you look at the fine-tuning services GPT and Gemini offers, they only offer you fine-tune for LoRa. So what that means is that you have every user have the shared W0. This is probably GPT-4, right? And then I go to ChatGPT, I go to GPT API and I say, I want to fine-tune. And then GPT says, I'm going to do a low-rank update for me. And then each of you actually have your own low rank updates. You have A2, B2 up to AK, BK. And now the saving here matters because this part is shared, right? Like everyone shared the same part. And if each of us only costs another like 100 million parameters, then maybe we can serve like 1,000 of these users and still like only like probably 10 billion parameters. But if each of us have to have a full matrix W, then it's too much memory. So basically this allows you to have multiple users, low rank updates adapter, in the same, memory. So that, you can serve multiple users and you can actually swap between them very fast. So in the inference time, you just say, if this user comes, I'm going to use this A1, B1. And if another user comes, I'm going to use A2, B2. I'm going to preload all of the users, maybe not all of the users. I'm going to preload a large fraction of the users adapters in the GPU so that I can swap between them very fast. And even I don't preload them in the GPU memory, I can still load them from CPU. So, and loading a small matrix, a low rank matrix is much faster than loading the full matrix. So in my opinion, that's probably the major benefit of LoRa, which you can serve many users.